So hello everyone, and welcome to the RQI-Online sessions. Special welcome to anyone who's managed to stay here from the first session, which would have been the middle of the night here. Yeah, I guess this is late at night for you guys. So we've got a very interesting set of talks this morning. So we're going to start with Sungyeon Bak. Can you share your screen, Sungyeon? And I need to
we may have to allow that.
Hang on. They may manually unmute him too.
Thank you.
Can you hear me?
Yes, we can hear you.
We can hear you.
So Sungyeon, if you can, would you like to be able to take questions during the talk, or do you want to save them to the end?
I would like to get a feedback in the end.
Sure. Okay, so if people would like to ask questions as they're going along, just raise your hand using the reaction icon, and I'll alert Sungyeon to that there is a question. Okay, so let's take it away. So this is Holographic Teleportation in Higher Dimensions by Sungyeon Bak, who's at the Gwangju Institute in South Korea.
Okay, thank you for introduce, and thank you for having me and giving me an opportunity to talk at the RQI-Online. My name is Sungyeon Park from GIST in Korea. Today, I'm going to talk about holographic teleportation in higher dimensions. Here, holographic teleportation means the traversable wormhole in holographic principle. Here is my collaborators, Yongjunan and Myungjunan, Victor Yanke, and Professor Kyung Kim. First, I would like to give you an outline of the talk. First, let me give you an overview of the idea, and then let me introduce our gravity setup and our interest. Then I will introduce some technical details of the computation, and then give you a result. First, let me give you an overview of the idea. Gao and Jeffrey and Walsh first considered a two-sided BTG black hole, which is dual to maximally entangled state in boundary. This can be understood as a ER equal EPR conjecture. Then consider the signal from the left side, then it cannot touch the right boundary. This means the left and the right side of the bulk is causally disconnected. To send a signal, consider the boundary perturbation, which may shift the horizon in the bulk. Here, the orange line means the shifted horizon, and the OL and OR means the boundary perturbation, which has non-local effect. And the red line means the negative shock wave. I will explain it more detail later. When we consider this setup, one can send the signal from the left side to the right boundary. This is the idea of the traversable wormhole. Interestingly, the signal link protocol of the traversable wormhole can be viewed as a quantum teleportation, in the sense that we should prepare the entangled state for each side, and we should conduct a measurement in the sense of quantum teleportation. Let me give you our gravity setup. We would like to generalize Gao and Jeffrey and Walsh setup in higher dimensions. To generalize in higher dimensions, we consider the Lindler-Edis T+1 spacetime. The action and the metric is given by this form. Note that the boundary geometry of the geometry is hyperbolic space. We consider this hyperbolic space because we have an analytic expression of the bulk to boundary propagator, which is the building block of the holographic principle. So we could get the analytic expression of our result. Then we can prepare the entangled state on the boundary, which is dual to maximally entangled extended geometry. This is known as thermal field double state. Consider the original geometry first. Then the geodesic distance is given by the form of Cauchy-Ton. And the bulk to bulk propagator between 2 points in the bulk is given by this form. Note that there is a geodesic distance dependency here. And then this is our first building block of our computation. We obtain the bulk to boundary propagator by taking one of these 2 points to the boundary. Then the bulk to boundary propagator is given by this form, which has a geodesic distance dependency here. This will give us an interesting result in the higher dimensional setup. So far, we prepared the entangled state in the 2 boundary. Then we need to induce boundary perturbation, which is known as double trace deformation. This is given by the non-local interaction between 2 boundary operators, which lives in the hyperbolic space. Then this causes the shift of the horizon by delta V. Note that this is directly related to the negative value of average null energy. For traversability, the delta V should be negative. And the average value of average null energy, when the average null energy has a negative value, it means the Planck violation. In this regard, traversability is constant with Planck violation, so we will focus on the Planck violation. Let me give you more detail about this relation. We could start by considering the linearized Einstein equation with the deformed geometry H mu field. This is for the Lindler ADST plus 1 geometry. And the right side, the stress tensor TUU is given by the boundary perturbation. So when we consider the integration along this line, along the null trajectory along the horizon, then this connects the shift of the horizon and the average null energy. In this regard, we could consider the traversability is constant with the Planck violation. How to compute Planck? Maldesna and Stanford and Yang first consider the signaling process as scattering picture. This is different from the Gao and Jeffrey and Wall's picture. We will treat this method. Look at the right picture. The blue line means the positive shock wave as a signal, and red line is the negative shock induced by the double trace operator, OL and OR. And we consider the coupling of these 2 shocks. Consider the commutation relation between 2 operators here. Then the non-zero value of the commutator means the correlation between 2 boundaries. Note that there is an effect of a negative shock on the right operator. For convenience, consider the two-sided correlation function with the effect of negative shock here, then its behavior is equivalent to the commutator. So we can measure it to compute the traversability. Interestingly, one can read off the annex in the phase shift of the correlator. We will explain this in more detail. More conveniently, we can see C tilde, which is a phase shift of the C. Then we can view that C1 tilde, we can, for simplify, we can consider the small h expansion in the first order. Then C1 tilde is a 4-point function. This is very similar form of with the out of time correlator, OTOC. Then in this regard, we can write C1 tilde as a scattering amplitude from in state to out state. After that, we expand the in state and out state in a basis of momentum in the UV direction and transpose position, which is live in hyperbolic space. The component is described by wave function, and the basis is normalized by this form. Then this is related to our starting point. Because our starting point is the worked boundary propagator, which we derived in original geometry, and the Fourier transform of this worked boundary propagator is the wave function. So we could compute the wave correlator analytically by using the worked boundary propagator. To proceed further, the Iconal approximation is important because we should consider the scattering amplitude of these two different Hilbert space. The Iconal approximation means the gravitational coupling are dominant in scattering process. Then the difference between two bases can be encoded in the phase shift in this exponential to the I delta. This means that the in-state and out-state lives on different Hilbert space, but when only the gravitational couplings are dominant, then the difference can be read off in this phase shift. Also, the phase shift is obtained by the crash correction, which includes the information of interaction between positive and negative shock. Here, the HUU minus means the deformed geometry from the negative shock, perturbed geometry from the negative shock, and T plus UU means the stress tensor of the positive shock. This means that we would like to view the negative shock as a background geometry and the positive shocks as the matter lives on the background. When we take the case of localized shock, then the positive shock wave stress tensor can be written by this form. They exist along V equals 0 line and localized at chi plus in transpose coordinate. And the negative shock stress tensor can be written in similar way. And there is a difference between their momentum. Then the corresponding deformation on the geometry is obtained by the replacement by the gravitational field in first order, HUU field. And we can write the ansatz of the HUU field as this form: U direction delta function and transpose profile, which satisfies the following profile equation. Then we can solve it and then obtain the gravitational field of the negative shock. By using these two things, we can calculate the phase shift of the correlator. This is the technical detail of the our computation. Return to the correlator. The shaded part is the first order expansion of order H. H is the coupling constant of the double trace deformation. And then we should consider all order in H. Then one can show that the result exponentiates as this form. Then we can integrate in the momentum direction and assume the localized case. Then the D term can be expressed by this form. Note that in the denominator, there is a transpose profile dependency. This is very important point in later discussion. And it is important that the transpose profile is depends on geodesic distance between positive position of positive shock and the position of negative shock. Second, for convenience, we also consider the probe approximation. This means that the backreaction of the signal is too small to deform the originally perturbed geometry. This can be calculated by the small scattering amplitude, delta. Then we implement this approximation by the first order expansion of G and Q. And the D can be expressed the D0 term and the D1 term. Here, the D1 term has a transpose profile and geodesic distance between positive and negative shock dependency. But D0 doesn't have this dependency, so we could calculate it as a constant. This affects the full correlator. The correlator in the probe approximation can be written as this form. In the shaded part, e to the minus iv is cancelled by the d0 term. Then we can see that there should remain a d1 term here. And q can be expressed as a momentum operator acting on the operator of the positive shock wave. Then in this regard, we can read off the annex in the correlator. As a result, we could obtain the analytic form of annex in higher dimensions as this form. Look at the plot of the annex versus conformal dimension delta. There is a specific conformal window of conformal dimension for each dimension. This is because we consider the relevant deformation in each dimension. So this is one point. And the other point is there should be a negative value in all dimensions. So we have proved that the annex violation holds for higher dimensions. In addition, we can calculate the full expression of the correlator. This is important in our future discussion, so keep in mind. Then I will explain, I would like to explain our results. First, consider the bound on information transfer. I will give you an overview in the previous discussion. Consider what happened when we consider the backreaction of the signal. Since the signal is the positive shock wave, this has an inverse effect of the negative shock wave. When we induce the positive shock wave into the black hole, then black hole's horizon should increase. And when we induce the negative shock wave with negative energy, then black hole horizon should shrink. In this regard, positive shock wave can offset the effect of the negative shocks. So in this simple picture cannot work when we consider the positive or backreaction of the positive shock wave. Instead, we should consider this picture. The exact calculation of backreaction of positive shock wave is very difficult, but when we consider this interesting idea, we can have some effective result. The idea is here. Instead of starting the original Lindl radius space-time, we can consider the starting geometry as already deformed by the total momentum of positive shock wave. Then the phase shift, the scattering amplitude of the from the negative shock is deformed, shifted by the total momentum of the positive shock wave. This is the idea. And as a result, I will give you an explanation briefly. This is the intuitional result. The y-axis is annex, shift of the horizon, and the x-axis means the total momentum of positive shock wave. When the total momentum of positive shock wave is increased, the backreaction of the positive shock wave increases. So then the annex saturates to the zero. This means that the wormhole geometry is closed. This is intuitional result. And in this regard, to send the signal, we should consider the two requirements. First one is small backreaction by the signal, as we seen before. And these requirements can be obtained by the probe approximation. This gives the lower bound of the momentum. The second requirement is the enough boost of the signal to pass through the wormhole. There is a required minimum momentum from the uncertainty principle. This gives a lower bound of the momentum. And when we consider the number of bits by the total momentum divided by each momentum, then this gives a upper bound of number of bits. As a result, when we consider these two conditions, the bound on information transfer should have a upper bound. In the previous researches, this is bounded by the entropy of the black hole. Then, to consider our case, we have a probe approximation result. The different thing is there is a dimensionality in the probe approximation. Then the bound on information transfer in dimension D with the uncertainty principle can be written by this form. But the dimensionality in the probe approximation is cancelled out by the delta V term. However, note that we also have a dimensionality of ANEC. We could found that the absolute value of ANEC is decreased for increasing space-time dimensions. This could be found by numerically. We could find the numerical result when we observe the maximum point of the absolute value of ANEC. Then this decreases as order 1 of D. This means that as a result, the number of bits should be bounded by this dimensionality. So as a result, we could find that in higher dimension, there should be also bounded by the entropy of the black hole and additional effect by the dimension. This is the first result of our work. And we want to consider the traverse wormhole as quantum teleportation, in the sense that there should be an entangled state and there should be a measurement process. We have explained the entangled state, and in this, from now on, I will talk about the what is the measurement in the traverse wormhole protocol. We can count the change of energy of the CFT by the double trace deformation. Consider the boundary Hamiltonian and their expectation value. This is a Schrodinger picture, but when we consider the time evolution as this form with the deformed Hamiltonian, perturbed Hamiltonian, then we can convert it to the Heisenberg picture. When you use the KMS condition, we could get the expectation value of change of energy by the bulk to, time derivative of bulk to boundary propagator. So we could get the following results. And interestingly, by the first law of entropy, the change of energy is proportional to change of entropy in the bulk. So we could find that entanglement entropy between two sides of geometry reduces for this case. This case means the when we consider the interaction of the double trace deformation, turn on at t equals 0 and turn off t equal f, and this should be upper than 0. Then in this case, delta change of energy is negative, and the entropy, change of entropy has a negative value. Since the measurement process has a decrease of the, goes through the decrease of entropy, in this sense, we could think that traversable wormhole protocol has a measurement process, should be. In this regard, we can describe traversable wormhole as a quantum teleportation. Okay, let's consider the final result. First, consider the homogeneous. I would like to consider the homogeneous and the localized perturbation. The left side is homogeneous perturbation, which is we induce the positive shock wave as local and the negative shock wave is homogeneous in the theta direction here. Theta direction means the transverse direction. When we consider the localized perturbation, then we consider the negative shock wave as a localized perturbation. We will consider this picture, and for the profile, transverse profile, there is a difference. For the localized perturbation, there should be a geodesic distance dependency. And more interestingly, the coefficient of this geodesic distance is butterfly velocity dependency. This is proven in our in the previous researches in our group in Lindler ADST +1 geometry. So this is our motivation to consider the higher dimensions in the traverse wormhole, because this is related to the scrambling effect, which is one of the measure of quantum chaos. Also, when we consider the homogeneous perturbation, the transverse profile is written by the constant term. Consider first the homogeneous perturbation. Then, in this correlator, the D1 term means the effect of the negative shock wave, deformed geometry. And in homogeneous case, this is given by the constant. And consider the time scale, which is known as scrambling time. This is written by this form in the sense that the shaded line, shaded part, D1 should have an order of shaded part. This means that we focus the zeros. When the denominator is 0, the boundary perturbation dominantly contribute the non-zero value of the correlator. So we need to the location where the denominator is 0. So this is related to the scrambling time, where the correlator has a maximum value. We focus on the geodesic distance between two positive shocks because the negative shock is homogeneous. For betting t right time for right perturbation, and when the left time is fixed, then the result is here. We can view the zero and non-zero part of the correlator. This means that in non-zero part there is a correlation. In more cases, we can read of the zero regions even for very early time. Then interestingly, even at the very early time, the correlation should be appear after the specific time. This can be interpreted as scrambling time, where the effect of the boundary perturbation first arises. This is very strict constrict. Consider the localized shock. As before, shaded part is the boundary perturbation term, and we need to see the zero line of the denominator. Then we consider the different cases. The boundary perturbation is localized at t equals 0 and x equals 10, which is denoted as red line. Then shaded line, shaded region should have a non-zero value of the correlator. The interpretation is here. There should be a scrambling time where the effect of the boundary perturbation first arises, and moreover, the causal inferences of the boundary operator propagates by the butterfly velocity VB. This can be read off by the orange line, which means the zero line is dominant, has dominant effect. This is given by the set point approximation. Let's consider the previous work. Koch and Asles and Naujen and Schwinger and Shu consider the this setup in BTG geometry.
Sung,
then
you are now entering your question time.
Okay. Okay, so this is the result, and thank you. Please.
So thank you very much, Sung, for a very interesting talk. So the talk is now open for questions. I might just start. So I'm trying to, so you argued that this is like a teleportation because there's an effective measurement going on.
Yeah.
So one thing I don't understand, so in a teleportation, the result of that effective measurement or the real measurement in an actual teleportation protocol has to be transferred over to the other side, so to speak, before you can recover any information from the probe, so to speak. How does that work in this analogy?
Yeah, thank you for the question. And I think this measurement is conducted on the boundary because we computed the entropy on the boundary. Then this means that the left boundary and the right boundary has a non-local effect and affect each other. So I'm not sure 100 sure, but it is related to your comment.
Okay. So, and sorry, you sort of skipped through the last bit about the scrambling time very quickly, but your conclusion was that that information can traverse through the wormhole. Is that correct?
Yeah. There
Okay,
should be
that's
some time, specific time to have an because in the shaded line has a effect of the boundary perturbation, which renders the wormhole traversable. In this regard, there should be a time to reappear the information.
Thanks. Any other questions? Please put your hand up and I can unmute you.
The raise hand button is in the, you click on reactions and then raise hand and we'll be able to see it. So Danny's got a thumbs up. Maybe we should.
Okay, where is
No, Danny put his thumbs down. Okay. Oh, there's a question from Al. Hang on, you have to loud on it.
Yeah, I got it. Thank you.
Okay.
So my question maybe was a bit naive in terms of it's sort of about the base protocol. So for the setup for this protocol, you sort of have this two-sided correlation function where you create shock waves on both sides. So on both of these sides of the wormhole. And my question is, yeah, I'll wait till you get to that slide in the very, very beginning. I think the image is very helpful. Yes, this one right here. So my question is twofold. One, why do you have to create shock waves on both sides? And two, if you have to create shock waves on both sides, how would you even begin to coordinate something like that? I wouldn't think that you can.
For the first question, thank you for question. We should induce the both side shock wave because we first consider the entangled state in both sides, and we should interact them. When we cannot consider the interaction between two boundary, then the left and right side of the bulk cannot connect causally. So we need to this double trace deformation. In this regard, we should interact between two sides. So this is, I think, the answer for the first question. And can you say again the second question?
I can definitely repeat my second question.
Yeah.
All right. So it sounds like this shock wave on both sides pushing in the boundary is required. So my question is this: if the shock wave is required on both sides, how can you coordinate that since the two regions are initially causally disconnected? So essentially, how do you create this protocol to communicate if you cannot communicate?
Yeah. Yeah. I think I can't answer this question now, but this is my previous question. Yeah. My ongoing question. Yeah.
Yeah.
This is just a possibility, theoretical possibility for wormhole traversable, but I don't know how to realize or coordinatize it. I don't know about it. Yeah.
Yeah, me too. I think it's very interesting though. Thank you so much for the talk. I thought it was very helpful.
Thank you very much for your
question. I guess it's not impossible to imagine a situation where there was a prearranged situation where it was prearranged that you would do something on both sides of the causally disconnected region.
Yeah.
Were there any more questions? Please put your hand up if you have a question. I think Danny wanted to ask a question.
Yeah, just to make sure, the perturbations, the shock waves, those are considered as some fields propagating on a given background. So you are not including the back reaction, so the way they modify the space-time structure, or you do? That's something that I'm not entirely sure.
Thank you for the question. In the previous cases, I consider the back reaction of the negative shock. In this picture, the orange line is the deformed horizon. This is made by the back reaction of negative shock. And in other point, in this picture, we don't consider the back reaction of the positive shock of the signal. Yeah.
Oh, okay. Thank you.
Thank you very much.
Okay, so I think there doesn't seem to be any more questions. So let's.
Hey, Tim, there's a question or a comment from Shoonoe. They say so in the chat.
Well, he hasn't put his hand up though. Yeah, please raise your hand if you have a question. Anyway, it's probably time to move on now. So let's thank Sung again.
Thank you very much.
Okay, so our next speaker is Sebastian Merk. And oops. Okay.
Hello.
So, hello. So perhaps you can share your screen, Sebastian.
Yeah. Let me try. All right, is that working? Can everyone see the screen?
Yep, that looks great. Thanks.
Cool. Can everybody hear me too? Or do I need to adjust my microphone? Am I too loud or not loud enough?
No,
that sounds good to me.
Great. Yep.
Sounds good. Okay, great.
So let's proceed. You've got half an hour and then 10 minutes for questions. I'll let you know when your half an hour is up. This is Sebastian Merk is our next speaker from Macquarie University, and he's going to talk about spherically symmetric black holes in semi-classical and modified gravity.
Yeah, great. Thank you, Tim. Yeah, so my name's Sebastian. I'm doing a PhD at Macquarie University and the newly established Sydney Quantum Academy. And before I get started, I would like to thank Nick, Tim, Eduardo, Rick, and anyone else involved for their efforts that went into moving RQI-Online and organizing the Australian and Canadian sessions of this conference. Many of the conferences I'd planned to attend in the second half of last year and the first half of this year as well have been canceled due to COVID. So I was really happy to hear that RQI will take place nonetheless, even if it can't be in person. Now, as you can tell by the title, I will be speaking about black holes and spherical symmetry. And this is work done in collaboration with Rob Munn from UWaterloo and the Perimeter Institute for Theoretical Physics, Valentina Bacchetti from RMIT in Melbourne, who will give a talk about entanglement harvesting in the last of the 4 Australian sessions, and my supervisor, Daniel Turner at Macquarie University in Sydney. And to give some motivation for the work that I'm presenting to you today, I want to start off by looking at the informationless problem, because I think it will be familiar to many of you, and it's an interesting problem from an information theoretic perspective. So the scenario here as follows. You imagine that you have a bunch of matter falling into a black hole, which I've indicated here schematically by the box, the pizza, and the apple falling into a black hole. The black hole then grows. But actually, Stephen Hawking has shown in his seminal paper from 1975 that black holes can also shrink by emitting radiation. And moreover, he has shown that the radiation that is emitted in that process is completely thermal, which means it's uncorrelated and it carries no information about the black hole other than the mass and the temperature of the black hole. So the conundrum here is the following: if the black hole evaporates completely, then all that I'm left with is this thermal radiation. So there's no information left about what went into that black hole. But quantum field theory tells us that information has to be preserved because it's a unitary theory. And this is the dilemma of the informationless problem or informationless paradox. Now, a necessary ingredient to get this paradox is that you must have a horizon that forms in finite time of a distant observer. Often that observer is referred to as Bob. And so the question of whether or not we actually have this paradox to begin with can be phrased as a question of what kind of gravitational collapse actually occurs in nature. So let's have a look at possible scenarios for gravitational collapse. And the first option is that an apparent horizon forms in finite time of Bob. And this can be followed by other events such as the formation of an event horizon or evaporation of the black hole, but it's not a requirement. Then the second possibility is continued gravitational collapse, where the notion of a horizon is an asymptotic or T-infinity concept. And what is usually done here is that one defines a closeness parameter, for example, the coordinate distance between the actual physical radius and the horizon radius. And then one can monitor this parameter until it reaches some prescribed very small value at some finite time of an observer. And then option number 3 is the formation of a transient object due to evaporation or some other reason, where again, you monitor this closeness parameter, it's reached in some finite time, but then it increases after. Now, from what I've said on my previous slide is that we need a horizon in finite time of a distant observer to have this paradox to begin with. So this means that in the scenarios 2 and 3, there actually is no paradox. So this is unproblematic from an information loss problem perspective, because there is no paradox to begin with. And because of that, the scenario I'm going to focus on in my talk today is the first one, where an apparent horizon does form in finite time of a distant observer. And it is a known result that this cannot happen unless the null energy condition is violated. And I've given a reference where this result was derived explicitly without making any assumptions about the asymptotic nature of spacetime. So our approach is the following. We make only one assumption, and this assumption is that a regular apparent horizon forms in finite time of Bob. And what regularity means in this context is that the two simplest curvature invariants that you can construct from the energy momentum tensor components are finite at the horizon. So they can have arbitrarily large values, but they cannot be infinite. Now, to distinguish the 3 collapse scenarios, we need to know what their consequences are. And once we know their consequences, we can compare the expectations for the respective geometries. And of course, our hope is that we can resolve those differences in future observations. So the goal of our study is to find out what the geometry looks like near the horizon if we make no other assumption other than a regular apparent horizon forming in finite time of a distant observer. We are working in the framework of semi-classical gravity, so I want to quickly explain what this means. One of the great insights of Albert Einstein was that the geometry of spacetime is the manifestation of the gravitational field. And in his famous paper from 1916, he put this notion in a precise mathematical form through the formulation of what we now know as the Einstein field equations. And so these are equations that relate the geometry of spacetime to a distribution of energy and matter. And actually the reason you can treat matter and energy on the same footing here is Einstein's other famous formula, E equals mc squared, which is a specific case of the more general formula for relativistic energy. What this formula tells you is that energy and matter can be transformed into one another. So we can treat them on the same footing. Now, what does semi-classical gravity actually mean? What it means is this: we are working with the expectation value of the energy momentum tensor, and what it does is this: it allows us to take into account quantum effects, at least on the right-hand side of the equations. And this is crucial for discussing basically any scenarios where quantum effects are important. For example, black hole formation, black hole evaporation, and so on. And usually what people do here is they specify a quantum state, and then you have to work with the renormalized energy momentum tensor, which can be quite tedious. But here what we do is we do not assume any specific matter content or a specific quantum state. So our goal is simply to investigate a generic scenario and see what statements can be made without making any additional assumptions. Now we're working in spherical symmetry, and a generic spherically symmetric geometry is defined by the infinitesimal line element, which I've written down here, where this function f of tr is defined as 1 minus c over r. And this function c here is what is known as the Misner sharp mass, which is an invariant definition of the mass. So that's very convenient because it will be the same across different coordinate systems. And this is one of the two metric functions. And speaking of coordinate systems, the other metric function here is h, and h plays the role of an integrating factor in coordinate transformations. For example, here I've given the generic transformation between tr and vr coordinates. But so what does spherical symmetry mean when we look back at our Einstein field equations in semi-classical gravity? Well, another way to specify the geometry is to write down the metric tensor explicitly. And you can do this directly by looking at the line element. And you will see that in the spherically symmetric case, it has a diagonal form. And the other important thing to know in spherical symmetry is that angular components won't give you any useful information. So this is the purple box here. So we can actually completely ignore that and not worry about those equations because there's no useful information that can be obtained from there. So to get the Einstein field equations in spherical symmetry, it actually suffices if we look at the TR block here. And you will notice that the off-diagonal elements are 0. However, the Ricci tensor components, TR and RT, are not 0. So you still get equation for those components. However, you can make use of a symmetry property of the Ricci tensor that allows you to write the equation for the two equations for the TR and the RT components into a single TR equation. So in total, we end up with 3 equations here for the TT, the TR, and the RR components. And these tau functions that you see appear on the right-hand side of the spherically symmetric Einstein equations are simply defined in terms of energy momentum tensor components. And the only purpose of using this specific definition is that it makes certain equations easier to deal with. And that is really all there is to it. There's no other reason for defining these functions that way. Now, I want to mention some previous results that we already know, which also motivated our current research. And all of these can be obtained without making any assumptions about the asymptotic nature of space-time. Now, I've already alluded to the first one in my introduction, which is that the violation of the null energy condition is necessary to obtain revalued solutions of the Einstein field equations. Now, the second reference here that I've listed includes higher order terms, and it also discusses black hole evaporation and the thin shell collapse scenario. And the third result that I want to mention here is from one of Danny's papers that was published last year. And what we've learned here is that the case of continued accretion inevitably results in a firewall that violates the quantum energy inequalities. And what that tells us is that once a physical black hole has formed, it can only evaporate. Another very important result for what I'm presenting today is that there are only 2 distinct classes of solutions to describe physical black holes. And with respect to the curvature invariance that I have introduced earlier, when we talked about what it means for a horizon to be regular, these 2 classes correspond to 2 different values that this parameter k can take on. And k is the parameter that sets the scaling for these tau functions which are essentially the energy momentum tensor components, as a function of f, which is defined as 1 minus c over r. The first new result that I want to present is an explicit expression for the transformation between VR and TR coordinates near the apparent horizon. And I want to first introduce this parameter x as the distance from the horizon. And we can define that in TR coordinates, and in VR coordinates, we've defined it equivalently and called it y. And the reason VR coordinates are extremely useful is that they provide a natural description of dynamic black holes, which is non-singular. So for example, for evaporating black holes, we can use VR coordinates. This is actually the most convenient set of coordinates to use for evaporating black holes. If you were to look at accreting black holes, you could use UR coordinates. So advanced and retarded null coordinates, so to speak. So how do we obtain an explicit expression for the transformation? I've already introduced the generic transformation between TR and VR coordinates. And then what we can do to get an explicit expression is to consider ingoing null geodesics. And by combining the two equations, you can actually write x as a function of VR. And this gives you the explicit transformation between those two sets of coordinates. And that is valid in the vicinity of the apparent horizon, I should mention. Now, speaking of coordinate transformations, we also know that there is a set of relations between energy momentum tensor components that relates the expressions we have in VR coordinates to the ones that we have in TR coordinates. And those are the three equations that I've written down here for the VV, the VR, and the RR component. So the ones that we need for spherically symmetric settings. Now for the K1 class of black hole solutions, the taus scale as f to the power of k, where k is just 1. So they scale with f. And if you write it down explicitly, this is what they look like at leading order. It's just EF, PF, and phi f, where physically speaking, E, P, and phi correspond to the energy density, pressure, and flux at the apparent horizon. And what is written below is just a generic form of the Misner-Sharp mass in VR coordinates, where remember r minus r plus is y, so the distance from the horizon. Now, as it turns out, it is not possible to satisfy the first relation between energy momentum tensor components in VR and TR coordinates unless the linear coefficient W1 is 1. And what this means is that if we define a function delta V as C in VR coordinates minus R, then this function necessarily changes sign at the apparent horizon. And this sign change tells us that there can't be a y squared component in the Misner-Sharp mass in VR coordinates. But now also remember that this Misner-Sharp mass is invariant. So expressions for the Misner-Sharp mass in different coordinate systems have to coincide. And if we compare the two expressions from TR and VR coordinates, we can look at the coefficient for the y squared term, and we know now that this has to be 0. And as you can tell from this expression, there's only one way to get a 0 here, which is the energy density being equal to 1 over 8 pi rg squared. So what this means is that we have identified a unique solution for the K1 class of solutions that is consistent with the spherically symmetric Einstein field equations. So what does this imply for the formation of physical black holes? Well, to answer that question, we need to ask when and how do the first marginally trapped surfaces appear? So let's assume that the first marginally trapped surface appears at some Vs. And it is then possible to show that for values greater or equal to Vs, the Misner-Sharp mass just corresponds to the expression we have for the K0 solution. On the other hand, if for values smaller or equal to Vs, we can show that there's a requirement for the derivative of this delta V function that we've introduced on the previous slide to be 0. And to satisfy that requirement requires W1 minus 1 to be 0. And that just means W1 is 1. So this corresponds to the K1 solution with extreme energy density that we have found on the previous slide. So what this implies is that at the very instant of its formation, a physical black hole must be described by this extreme K1 solution, and it then immediately switches to the K0 solution. And just as a side note, we were also able to provide arguments to show that these two classes of solutions are the only possible perturbative solutions in modified theories of gravity as well. Now, the last result from this paper that I'm going to show you today concerns generalizations of surface gravity. Surface gravity plays an important role in both general relativity and semi-classical gravity, but it cannot be defined unambiguously in stationary in dynamic spacetime. So it's only defined unambiguously in stationary spacetimes, where it is proportional to the Hawking temperature of the black hole. Now the question is, well, is there a sensible way to generalize surface gravity for dynamic spacetimes? And it is known that Hawking radiation does not require the formation of an event horizon or even a parent horizon. But either way, what we can do is we can relate the pre-Hawking radiation to the peeling property of null geodesics, where this equation here is just the previous equation for ingoing null geodesics. And actually, the peeling surface gravity is defined as the linear coefficient in the Taylor expansion of dr over dt. And now what we found in our recent article is two things. The first one is that in VR coordinates, it's actually impossible to perform such a Taylor expansion with the metric functions of the VR coordinates. The second thing is that to be compatible with this equation for null geodesics, the peeling surface gravity would actually have to become infinite at the apparent horizon. And this is a very interesting feature that I will come back to after briefly discussing some observational data. So especially in the last couple of years, we've seen a plethora of observational evidence for astrophysical black holes. For example, 4 to 4.5 years ago, we've heard about the detection of gravitational waves that were emitted in a merger of two black holes announced by the LIGO and Virgo collaborations. And you might remember a year and a half ago, the Event Horizon Telescope published this image here, which shows a light ring surrounding what is supposedly a black hole. And actually, this result has since been superseded by their latest study from October 2020, so 3 months ago, where they have used the observational data to place constraints on how significant a deviation from general relativity can be while still being compatible with their observational data, because the size of this shadow region depends on how strong gravity is near the horizon. So if it's stronger than what general relativity predicts, you would expect a larger size of this shadow region. If it's weaker, you would expect this region to be smaller. And then, of course, there's the confirmation of the existence of a supermassive compact object in the center of our Milky Way, which was achieved by monitoring the motions of stellar trajectories, and which resulted in half a share of the 2020 Nobel Prize in Physics for Reinhard Genzel and Andrea Ghez, with the other half awarded to Roger Penrose. Now, how does this relate to our research? Well, there are two models that can explain the observations of astrophysical black hole candidates. They can either be horizonless ultra-compact objects, or they can be genuine physical black holes with a horizon. And these physical black holes can have other classical features as well, such as a singularity, but again, not required. They can also be non-singular. They can be regular or non-regular. So there's many sub-classifications that one can make here. But the key question is, do these objects have a horizon or not? Yeah, so this is the title of our article that I've referenced here. Now, what our results in this article suggest is that if semi-classical gravity is valid, these objects are horizonless ultra-compact objects for the following reasons. The first is that we've seen it's not possible to find a sensible notion of a generalized surface gravity. That is to say, if there is a horizon, then the generalized surface gravity is infinite at this horizon. The second reason is that if we compare the required energy and timescales for horizon formation with the known semi-classical results, then we find that even if the necessary null energy condition violation does occur, the process is too slow to transform the objects into genuine physical black holes. And of course, this has important ramifications. For example, if you go back to the informationless paradox scenario, I mean, this scenario hinges on the existence of a horizon to trap information. So if there's no horizon in the first place, then information is never truly trapped to begin with. So if there's no horizon, then there's no paradox. Of course, there is one other option, which is you can say, well, I believe semi-classical gravity is fundamentally flawed. And then you can still have genuine physical black holes with horizons. But then to form these horizons, you require new, currently unknown physics. And one way to account for new physics is by using modified theories of gravity, where you have this additional modified gravity term that accounts for deviations from general relativity and semi-classical gravity. And this is actually what we've looked at here in a separate article, which I will talk about for the remainder of my talk. So this preprint that I've referenced here in the top right-hand side corner, we consider the modified Einstein field equations. And much like in the previous article, we make no specific assumptions. Here we make no specific assumptions about the modified gravity term. And the big advantage in keeping things generic here is that the results we obtain must apply to any and all possible modifications of gravity, irrespective of specific properties of a particular theoretical model. And now the question we set out to answer is, well, what are the constraints that any self-consistent modified gravity theory must satisfy to be compatible with the existence of physical black holes? And again, we do this assuming only that a regular apparent horizon has formed in finite time of a distant observer Bob. The derivation of the Einstein equations in spherical symmetry is straightforward, and I've written them down explicitly in the box here for the TT, the TR, and R components. But now what we have to consider also is that our metric functions C and H are subject to perturbative corrections, which we've called capital sigma and capital omega. And similarly, there's also a corrective decomposition of the energy momentum tensor itself. Then what we can do is perform a series expansion in lambda and keep only the first order terms. And then schematically, what we'll end up with is something like this, where the bar labels terms that can be expressed as a function of the unperturbed solutions. So this allows us to actually obtain the modified gravity terms as a function of the unperturbed solutions. So what we obtain for both types of solutions, the K0 and the K1 solution, are the decompositions of these modified gravity terms as a series expansion in X, which is the distance from the horizon. And in both cases, we find there's actually some terms that are divergent as you approach the horizon. And we were actually also able to obtain relations between the coefficients of these modified gravity terms. So the last thing I want to mention here is that we have checked whether or not these constraints are satisfied in the Strabinski model of gravity, which is a special type of F of R theory, where the gravitational Lagrangian density is modified by the addition of R squared. So instead of just having the Ricci scalar, like in classical GR, here you have R plus lambda R squared. So you have quadratic corrections in the Ricci scalar. And this is actually the simplest modification of general relativity, but nonetheless, this model actually has some relevance in cosmological settings, specifically as the first self-consistent scenario of inflation. And now what we found is that for the K0 class of solutions, all of the modified gravity terms have a structure that conforms to what it should be, and all of the relations between the coefficients are satisfied identically. And for the extreme K1 solution, we also find that the structures conform to what they should be. But here, in order to satisfy the relations between the coefficients of the modified gravity terms as well, additional constraints beyond what is required by the theory itself are required. Otherwise, you can't guarantee that this perturbative K1 solution exists. So I think I have about 2 to 3 minutes left, if that's correct. So I will move on to the summary to give you a quick rundown of our results. So what we found is an explicit expression for transformations between TR and VR coordinates near the apparent horizon. Then secondly, we've shown that there's only one dynamic K1 solution that is consistent, and this solution requires an extreme valued energy density. We've also seen that there's a unique formation scenario that physical black holes must adhere to if the horizon is to be formed in finite time of Bob. And this unique scenario involves behaviors of both the K0 and the K1 solutions. We've also tried to generalize surface gravity and seen that it diverges at the apparent horizon. And lastly, we have derived constraints for modified gravity theories, which must be satisfied to be compatible with the existence of perturbative black hole solutions. And for this last point 5, we have checked that the Strabinski model satisfies these constraints, even though in the extreme K1 case, some additional constraints are required to ensure the existence of the perturbative K1 solution. But there are no contradictions so far. Now, what is left to do is you can look at other more complicated modified gravity theories. The R² model, the Strabinski model, is the simplest extension of GR, but of course, the options are more or less endless here. You can add other terms to the Ricci scalar invariant, for example, square root R. You can even think of negative exponents or the Kretschmann scalar, which is a specific contraction of the Riemann curvature tensor, and so on and so forth. And I think my half hour is up, so I will stop here and open the virtual floor for questions. Thank you.
Thanks, Sebastian. Okay, we have time for questions. I might jump in first again. So you were saying that new physics was required to sort of retrieve the formation of the black hole. But this is in the context of analyzing it in semi-classical gravity. And I mean, isn't it possible that that's where the problem is? That just analyzing things by taking the expectation value of the stress energy tensor is not the right thing to do. I mean, there's been this work from Wang and Unruh lately arguing that the fluctuations in the stress energy tensor are so of similar size as the actual expectation value, and so you can't really just do that.
Yeah, so you're right, of course. So we work in the framework of semi-classical gravity. So if this is not the correct framework, then we can't rely on the conclusions that we draw from using this framework. But nonetheless, it is a very established framework that people use in contemporary black hole physics research. But of course, there is the option that this is not the correct thing to do, that it's wrong. And I mean, to some degree, people of course expect that it's a limit of a full theory of quantum gravity. So yes, it is an option to say semi-classical gravity is wrong, and we still have those horizons. But I mean, in a sense, you can also say maybe it's just easier to not have the horizon, because then you don't have to make additional assumptions, right, about to explain our current observations. But yeah, so those are the two options.
Thanks. Any questions? Please put your hand up using the reaction button. If you can't do that, just do a thumbs up. I think there's a thumbs up somewhere.
Let's show.
I can't see who it is though.
Oh, it's gone now. Any questions? There's a thumb.
I don't know.
Oh, hang on. We have to hang on just a minute. I have to allow people to unmute themselves. There we go.
Was there a question?
I have a question.
Yep.
So from like the early part of your talk, you assume like it's the space-time is spherically symmetric. And I thought that was an assumption, and I didn't really understand why you could make that assumption.
So the reason we make this assumption is because you can't solve certain equations in axially symmetric settings, or not in the same way. So for example, as far as I know, thin shell collapse you can only solve if you make these assumptions about the shells being infinitesimally thin and having spherical symmetry. But I should mention that some of the results that I've shown you from the slide with the previous results, let's see if I can go back to that actually, have been extended to axially symmetric settings as well. So there's a master student at Macquarie, Pravin, who has published a paper in PhysRFD together with Danny, where some of this has been generalized to axially symmetric settings as well. So in particular, you still get this violation of you still need a violation of the null energy condition to get real valued solutions and have an apparent horizon form in finite time of Bob to begin with.
Right, I meant more so without the assumption that it's spherically symmetric. So if it's not spherically symmetric, is it possible that these conditions you derive are not true, or?
No, like I said, so this condition here, the violation of the null energy condition, for example, has already been generalized to axially symmetric settings. And I believe, Danny, correct me if I'm wrong, the same is true for the firewall that violates the quantum energy inequalities. I believe that also has been generalized to non-spherically symmetric settings as well. But of course, you have to make some assumption about the geometry, otherwise you can't solve the Einstein equations. If you can't solve the Einstein equations, then all you have is doing something with like congruences and divergences in the sense of the Raychaud-Hurry equation, for example.
Right, I see. Okay, thank you.
Yeah, so spherical symmetry is just simpler, but if you make some assumptions about infinity, then it's a very old result of Hawking and Ellis that if you don't have violation of the null energy condition, then your apparent horizon is hidden behind the event horizon, and for all practical purposes forms at infinite time of the distant observer. Our spherically symmetric result and then modified is that we have higher symmetry, but we don't make any assumptions about infinity. So that's the difference. But at the same time, it's very consistent with the result of Hawking. It's just by doing some details, we showed in practice what goes wrong. And what goes wrong is that you get complex valued solutions if you try to force that you satisfy energy conditions.
Yep, okay, that makes sense. Thank you.
Okay, any other questions? We've still got a few minutes spare. I did have another question if there's nobody else putting their hand up.
Yeah, sure.
And that was, so you say there's no paradox because in this situation you're suggesting the horizon won't form. But that still leaves kind of unanswered how the Hawking radiation is modified by the fact that the horizon doesn't form. Have you thought about that at all?
I mean, if you want to observe Hawking radiation, I think to actually observe it, you need an apparent horizon finite time of a distant observer, right? If I remember correctly. So if you don't have that horizon, then you have to think about, well, pre-Hawking radiation, I guess. How would you observe that?
I guess I'm just going from an observational point of view. You're outside this thing, it's shrinking, so radiation must be coming off it.
Yes.
What does the radiation look like?
So yeah. The most common belief is that it starts because of the collapse, and as everything goes smoothly to, say, Schwarzschild-like black hole, this radiation asymptotically approximates Hawking radiation. And that's how the generalizations of surface gravity were proposed and shown that everything goes nicely if this quantity behaves nicely. So, so until we started to look at it, we thought that, yeah, it's just fully consistent. Now we see the problem that if the apparent, and you don't need any horizon to have this radiation, which will getting closer and closer to the standard Hawking result. And the only potential difficulty is that if we do assume that the horizon forms in finite time, then this quantity that presumably governs Hawking-like radiation diverges. Now we know that this quantity diverges if you stick to semi-classical physics at the last moment of evaporation. So it sort of hints that if you want full consistency, that means the horizon forms at the very last moment, according to distant observer. But yes, we have to look into how this result modified what we know, and how to mesh them in a big picture, in a general formalism. Because the easy answer, yeah, it's just another argument that horizon that basically for practical purposes horizon doesn't form, and we have pre-Hawking radiation that takes care of evaporation. But in practice, we need to do calculations. And the only things and only calculation in which we know that horizon forms in finite time, it's on the scale of evaporation, but shorter, because of the simplicity of a model, we have some internal contradictions, so that you can either point out as argument against, or to gloss over and say, yeah, you see, it forms. So we need more serious models.
Yep. There's one last hand up. I don't know if you want to do it.
Thanks for that. Yuri, did you want to quickly ask a question?
Yes, just a quick question. Maybe it's not so professional, but nevertheless. According to estimations, if we take into account the total mass of our universe and the radius of the universe, it seems that we obtain a black hole. Can you comment these estimates?
Sorry, could someone repeat the question for me? I didn't really hear it properly.
If we estimate the radius of our universe, and if we estimate the total mass of our universe, we arrive to the conclusion that we are living in the black hole. The relationship between the radius and mass corresponds to the black hole. Can you comment these estimates?
So none of our results contradict any of the known relations between the mass and the radius of the black hole. Did I understand your question correctly, or? But there's no contradictions here anywhere.
I'm not talking about contradiction. I'm talking just about the fact that we live in the black hole. The relationship between mass and the radius of our universe corresponds to the black hole.
Sorry, what's in the black hole? Can someone write it in the chat?
So the proposal is that the total mass of the universe and the radius of the universe are such that we should be living in a black hole. That's what the question, that's what the comment was. And the question was, can you comment on that?
Okay, sure. I can comment on it, but I think from our investigations, there is no comment that you can make about such a scenario. Because what would be an observational difference between us being enclosed inside the boundary of a black hole or not? There's no observational, I can't think of any observation that you could make to find out whether or not we're living in a black hole or not. So yeah, that would be my comment on that. Sorry if that's a bit anticlimactic or disappointing.
Okay.
Okay.
But anyway, thank you.
Thank you guys, appreciate it.
Thanks, Sebastian. Let's thank Sebastian again. Okay, so we've got, well, we were supposed to have a 10-minute break, but that's evaporated. Black hole joke there. Anyway, so
well done. Very good.
We're going to move on to.
You want to wait till 12:30?
Lauren? Yeah, we'll
11:30 rather.
Let's wait 2 minutes before 12:30 to start. But yeah. Colin, you might want to share your screen to get prepared.
It may be that some people will join in a minute and a half.
Yeah. Okay, Colin's just getting ready, so you can.
There's no hurry.
Stretch your legs for a minute.
Just checking, is that working?
Yep, we can see your screen and hear you quite clearly.
That's good.
We don't see any video though. We don't see any video. Yeah, turn your video on.
I'm actually a little bit haggard this morning. I was thinking of just staying video off, if that's all right. I know it's less personal. Yeah, I was actually watching the Canada talks until about 2:30 a.m. or whenever it was in Brisbane. So maybe that's one excuse for not looking 100% this morning.
That's very dedicated.
They were good talks, actually.
Good.
Yeah. Right.
Okay, so we'll get started now. So our next talk is by Colin McLaurin from the University of Queensland, and he's going to talk about hydrodynamic Hawking radiation.
Thanks very much, Tim. I'd like to thank the organisers for giving me a chance to speak. Apologies, that looks like a beautiful PDF normally, but PowerPoint doesn't seem to handle the PDFs very well. But anyway, so my talk is on hydrodynamic Hawking radiation. More generally, it's actually going to be a talk on, I guess, a hydrodynamic or fluid model of quantum mechanics a bit more generally. My research into the application to Hawking radiation is still ongoing, but you can see a sort of velocity field there, which will be a hydrogen atom, as we will see later. And this talk, aspects of it are still preliminary. I'm still working on them, and there'll be several points where I hope to get discussion from all of you, and I hope we can all learn something from the input. So my motivation, suppose you have some scalar field where for now it doesn't really matter what sort of wave equation it satisfies, but take the Schrodinger equation for familiarity, take the Klein-Gordon equation for something that's relativistically consistent or whatever. And so you might have a Gaussian there, where in this case the vertical axis is a probability density, and I'm drawing two spatial axes horizontally. And so you might think of you know, normalizing this thing in the usual sort of way, which you would want to understand it as a probability interpretation. You can probably particularly think of this as the Schrodinger equation for now. But if you think of it from a relativistic point of view, then different frames measure things differently. As we remember from introductory special relativity, you have things like length contraction, time dilation, when frames are moving relative to one another. So if you think of the original Gaussian as normalized in some particular reference frame, let's say it's Minkowski space, or let's say it's just, you know, Newtonian space, which is not really consistent, but anyway, then it would not be normalized in a different frame by the usual simplistic or naive application of what it means to integrate that scalar over a volume. So you can think of the bottom picture is the same wave function, but in the frame of observers moving extremely quickly to the right, say, and so it sees length contraction. And in this frame, according to this frame's definition of a three-dimensional volume, the wave function is not normalized. So this would seem to be a fail of the probability interpretation. There's just another few pictures of the same idea, the same motivating question. The picture on the right, I actually drew this and put it on Stack Exchange, hoping for an answer. No one's answered, not many people even looked at it. But in the right-hand side picture, I've drawn time on the vertical axis and a space dimension on the horizontal. And the bright stripes in the middle are probability densities. Think of it as like a Gaussian moving to the right-hand side in these coordinates. So that central white strip is the highest probability density, and it fades off a bit to the side. And the various colored lines, the red line, the green line, and so on, a different hypersurface you might consider this over. So we're probably more considering a Lorentzian space-time now. So some scalar field we're trying to interpret as a probability density in a relativistic context. So the green line, you could say, is representing space in the frame defined by our coordinates, you know, because it's just a horizontal line in our coordinates. And suppose our wave function was normalized over that green hypersurface. Well, the red hypersurface, still in that same picture on the right-hand side, this would correspond to a moving observer. And due to the contraction effects as seen previously, our wave function would not be normalized. The yellow hypersurface is a time-like one, and it actually doesn't even intersect our Gaussian profile at all. So the integral of the probability or the scalar will just be zero, which is definitely failing as a probability, it would seem. The black hypersurface would have a very large volume, so it's time-like. But if you correct for that sign, the integral over that hypersurface would be very large. Let's say it's 10, you know, and you see you have a total probability of 10, which is not very physical. So what to do about this? The idea is, you know, look for a conserved quantity. We want to get flow lines, which would be like a conserved flow, and then we'll be able to treat this very consistently in a relativistic sense. I should say that a lot of what I'll be saying you can find in textbooks, but I question if all the applications have been drawn out, just in case any of this, I'm not sure how this all will sound. That other picture to the left there, I've got 3 token world lines. So let's say these are particles, or they're a flow probability or something like that. And the blue line is a hypersurface. And the idea is to try to deal with this problem with the probability interpretation in a relativistic sense, is to have these conserved world lines, this conserved flow, and then intuitively think of counting how many world lines your hypersurface crosses. And so if we know these lines are conserved, then we know if we do this correctly that we'll be able to keep the probability interpretation consistently. So in the example here, our hypersurface goes from space-like to null to time-like and changes, and it's a mess. It intersects the middle world line 3 times. You'd think, well, that might overcount the probability density, but you can get around these issues by considering the orientation and so on. But the idea or the intuition is that by using a conserved flow rather than the scalar field directly, you can actually make this interpretation consistent. So an example, the Schrodinger equation. I'm sure that the concept of this slide will be familiar, whether or not the details are. So as you're well aware of the concept, probability is conserved for a wave function satisfying the Schrodinger equation. And what you can do is use the de Broglie ansatz and split it up into a real and imaginary part. That's the top equation on the right-hand side there. So rho and s are purely real. And then what you get is the Schrodinger equation splits into two separate equations. I'm not too concerned about how the phase part, the partial s by partial t, change with time. I'm more interested in the flow of probability, which is the change of this probability density with time. And so you can split the current up into this current J, into the density times the free velocity. And the free velocity is just given by the gradient of the phase. That bottom equation there, mu is the mass. And so that other bottom expression is the Noether current, which I'm sure will look familiar. So we can do the same thing for Klein-Gordon. The reason I'm using the Klein-Gordon equation is for simplicity. The Dirac equation, for example, is considered more favorably. I'm just using Klein-Gordon for simplicity. What you can do is do the same sort of thing. The current is the Noether current. These are now 4 vectors. For the Schrodinger case was 3 vectors. And this current is conserved, which are familiar sort of formulae. And so I want to interpret this current as a flow of probability. Now, this is normally criticized as unphysical. I'm thinking of David Tong's lecture notes on quantum field theory. He says that there's negative probabilities, towers of negative energies, superluminal trajectories, and so on. But there's some sources that are more positive. So I'm particularly thinking of a textbook by Greiner. Greiner has a lot of quantum textbooks, but Relativistic Quantum Mechanics, I think it's called. And he takes this single particle interpretation further, and authors say that this is okay if the velocities are not too high, the potentials are not too strong, and so on. And there's other books like Schwabel and Wachter that also do this sort of approach. What about other possible velocities? Because the aim is to get a conserved current to be able to interpret the scalar field physically. You know, if it's a real field, you get the usual stress energy tensor, which actually has the form of a perfect fluid. So this does single out a generally convariant or a relativistically consistent velocity, which is the gradient of the field. However, I believe it's not divergence free. And also, if it's a complex field, I'm not sure the usual stress energy tensor will actually yield any natural full velocity field in this way, and it doesn't seem to be conserved. So there's other possibilities, but it seems like the Noether current is a very natural choice. So I'm going to start with a hydrogen-like atom. I haven't finished my research on Schwarzschild space-time and the Hawking radiation, so I'm thinking of the hydrogen-like atom as a sort of simple analog of Schwarzschild. You've got a central Coulomb potential. I'm not considering gravity for now, but perhaps, you know, given the similarity in Newtonian physics between the Coulomb potential and Newtonian gravity, perhaps there's some similar properties to Schwarzschild space-time, which we will get to a bit later. What you do is you make the usual ansatz as an introductory quantum mechanics, that the wave function is separable into big T, big R, big theta, big phi, and you get the usual spherical harmonics. You get quantum numbers N, L, and M as usual, same as for the non-relativistic case. And the radial functions are, I forget the name now, the W functions, where I've put some dots to miss out a lot of terms. They're not important, but they're, what are they called? anyway, you get Whittaker functions for the radio ones. This probably goes back to the solution of the Dirac equation in 1928. It was just a similar solution. So now that we have this wave function for a hydrogen-like atom, which is a sort of hopefully analogy of a wave equation in Schwarzschild spacetime, I'm going to work out the conserved current, and you can work out the current of a simple a scalar like that. You can work out the current of the product, and we get the current of the overall wave function. When I put the current in parentheses, that's really because I just mean formally applying the formula for the Noether current to a particular part of the wave function. Anyway, what you end up getting down the bottom there, that current J is the Noether current for this Klein-Gordon hydrogen atom. And I particularly draw your attention to the more right-hand side. You got the T, R, theta, and phi components of this vector field. You can see there's it's flowing in the T direction. There's no flow in the R direction. There's no flow in the theta direction, and there is flow in the phi direction. The reason is that for the parts which are purely real, so the function capital theta is purely real, it ends up being that there's no Noether flow in that direction when the function is purely real. So there's no flow in the R or theta directions, at least for our particular set of solutions. And so what you get is the picture you saw before. Again, apologies, that picture really looks better when it's not in PowerPoint. But what it is it's the Noether current for this hydrogen atom that's flowing around. So it's flowing around the z-axis, and it's like a sort of big rotating ball. It's not rigidly rotating, but like a big rotating ball. This plot is the density times the velocity. If you just plot the velocity in this particular frame, the field looks sort of more cylindrical. It's more squished in at the middle, and it's more extended at the poles. And the point of this is to allow physical interpretation of the scalar field by getting this conserved vector field, which represents a flow. Man, I don't like the layout of my talk. Anyway, so first thing I'm going to get feedback on, I'm expecting and actually hoping for criticism on this, and we'll get to how this relates to the Hawking radiation, is you actually get superluminal flow for part of it. I'm just going to go back a slide. So towards the center, towards the z-axis, then the velocity actually gets larger and larger for this Coulomb field Klein-Gordon hydrogen atom. The velocity drops off as you get further away. And that picture should really be rotated. That's along the z-axis. And this is the surface at which the flow becomes the speed of light. I'm just going to present this slide, then ask for feedback. And so, there's obviously been discussion of superluminal flows, and the consensus is that yes, you can have things like, indirect abstract objects like shadows can move faster than light. You have an ant walking on a projector or whatever the standard example is. Phase velocities, group velocities. You often hear that group velocities must be less than the speed of light, but some people seem to say they can be greater. It probably depends on your definition. In entanglement, speaking to some RQI people at UQ, they didn't like the word faster than light or something, but they preferred a term like space-like correlations. But anyway, when you collapse an entangled state, or whatever terminology I should be using, it seems that something is happening faster than light, although you might want to use cautious language. Quantum tunneling is often said to occur faster than light, although the disclaimer would be that the speeds are not physically measurable or significant. On the other hand, the consensus also says, usually, that there's causal influence faster than light is not good physics, and you also can't transfer information. There's probably a caveat, like we're assuming quantum equilibrium or something like this. Just briefly before I invite criticism on this, yeah, most of the flow for this particular orbital is not superluminal. In fact, the proportion of the flow which is superluminal is only 10 to the power of minus 12, so it's tiny. And the average speed of the flow in the particular frame shown is actually only 1/700th of the speed of light. So even though we have a small amount of the flow which is superluminal, when you take averages, you do get very much subluminal, which may or may not be significant. But anyway, I just want to invite feedback, and I expect criticism on this aspect of the one particle interpretation of the Klein-Gordon equation. I'm sure some people will be criticizing superluminal flow. Possibly it's a debate that has already happened. I'm probably ignorant of some of the debates. I could be getting into something, I don't know. Anyway, comments, please.
So is that the end of the talk?
No, it's not the end of the talk. It's just partway through, and I was expecting people would have opinions on this.
Oh, I see. So you're soliciting questions right now. Tim,
Yes.
Tim, are you here? Do you want to manage this?
I'm looking. I don't see any hands up. I mean, I could make a comment, I guess. I mean, you sort of were motivating by talking about making slices at various different angles and therefore not conserving probability. I mean, the normal thing in quantum field theory is to always consider equal time slices. So when you change reference frames, then you also change what how you make your slice. And then, at least from the point of view of, probabilities of detecting particles and things like that, then things work out. So I guess I'm going back a little bit as to exactly the motivation for what you're doing.
That's a great comment, Tim, and something I actually intended to comment on, but I'm glad that you reminded me. Yes, we did cover some of this in the QFT course at UQ, and I'm just looking at an alternate approach. So I'm, trusting QFT, which is not my strong point. I'm coming more from a relativity background. Trusting that all works well. I'm just curious how far we can push the, this scalar field or this single particle interpretation. Actually, yes, I will be chasing this up later in the talk, but actually one of my questions was going to be to people, what are the particular differences that QFT would have with this approach? So, I suppose my motivation is just to, this seems consistent to me, and just to try to push it as far as possible, and push the interpretation further than people who do like this approach, like Greiner would push it. So yes,
Okay. There's another question from Yuri.
Yes, Colin, could you come back to the second slide and explain, please, not this one, previous. No. Slide number 2. Or maybe this is slide number 1. Yeah. No. Where the slide where you presented, yes, this one. No. Come back. Yeah, this one. So you stated that there is a transformation which does not conserve the total probability. And in the last formula, the probability is less than 1, the total probability. but it can be, maybe it can be related to the missing of Jacobian in this transformation from one coordinate system to another one, because the total probability should be invariant. What is your interpretation?
Yes, I did put a dash on the DV to indicate that this is the three-dimensional volume element with respect to different coordinates. But because of the length contraction in a different frame, if the scalar field were to be interpreted naively, just as it is, or its amplitude squared, then this would not be normalized along a different spatial hypersurface. That's the idea, and the fact that this doesn't work is the motivating factor to say that we shouldn't take the scalar field just as it is. We should instead get the conserved current and work with that instead.
But in such transformation, we have to take into account the Jacobian of transformation. So it's not a formula like this one. It should be also psi squared times Jacobian of transformation. And maybe with the help of that, we can obtain unity.
We are actually integrating over a different hypersurface. So I guess I'm thinking of the scalar field as being stationary, it's not changing over time. And it's actually not the same integral. It's actually over a different hypersurface. So I think that it's not the you mean if it was this integrating over the same hypersurface but changing coordinates, then there would be a Jacobian and you'll get the same answer, which I agree with. But in this case, it's a different hypersurface that we're integrating over. And we find that on that different hypersurface, the probabilities, or this naive probability, is not conserved.
Okay, so maybe the key word here is naive interpretation, naive approach. But
yeah, exactly.
Yeah, okay.
Yeah, taking the way you function just as it is naively doesn't work.
Okay.
We should get the conserved current and then use that to interpret the probability amplitude.
Okay, thank you very much. Now it's clear.
Thank you. Tim, if you're still there, what time do I finish? Sorry. Anyway, it must be pretty soon.
At midday is when your question time starts. I mean, you
no
can
worries.
do that, but because you're having questions as you're going along. There doesn't seem to be any more questions at the moment,
Yep.
so maybe you should proceed.
I'll head on, thank you. So this lets us do consistently things like averages. So instead of just naively integrating some field, call it alpha there, over the volume, we now integrate the 0th component of the conserved vector field. I'd like to write it more generally than this. This looks very sort of coordinate dependent by putting it J0. But what I really mean is use the divergence theorem, look at the flux across a boundary or across a hypersurface, and this will be a consistent way to do averages. So just like we were talking, the probability is not conserved if you just naively take the scalar field. In the same way, things like averages, which are the integral of something times the volume over the integral of the volume, these would not work consistently either unless you use the conserved current instead of the field naively. So that's the sort of application there. Space-time splitting, important to understand the relation between four-dimensional space-time and connection to physical observables. Last time I looked at the volume of black holes as given by various different observer fields, same sort of idea. Yeah, let's just skip over that. The hydrodynamic interpretation I've basically explained. It's like Bohmian mechanics, but I think there's a philosophical difference. In Bohmian mechanics, it takes a single trajectory as the real one followed by a particle, whereas the fluid or hydrodynamic interpretation just takes all the possible trajectories as like a flow of probability. Schwarzschild space-time. So the Klein-Gordon equation has been solved for even Kerr-Newman plus a cosmic string going through it plus a magnetic field and so on. So the Klein-Gordon has been solved in various space-times in terms of the confluent Hewn functions. And so it might be, to look at Hawking radiation, people have tried to do scalar fields as a model of Hawking radiation. So by the approach I've tried, if you can find a scalar field solution, then you can get a description of Hawking radiation. You can work out the physical effects measured by different observers. So you could ask, for example, suppose I have an observer that's free falling at some given rate or with some given energy per mass. What would be the flux measured by that observer? Then the calculation remains to be done, but you would probably not get just a simple Doppler shift formula, you know, thinking of 2-point particles meeting and having a relative velocity, then just having a Doppler shift between them or something like this, because the description would not be of a single little point particle, but actually a whole wave or field. And I expect you'll get some sort of novel effects based on that. Oh boy, I feel like I've missed some slides, but anyway. That's something else I want to say, actually. Going back to the Coulomb field in Minkowski space-time, Klein-Gordon equation, if this works as a sort of analogy for Schwarzschild space-time, in other words, if the sort of solutions you get are qualitatively similar to the ones you'll get in Schwarzschild, I'm still working on understanding the solutions. They're a bit of a pain, to be honest. Perhaps this would solve, and the whole superluminal trajectories thing, when you're very close to the z-axis, this could even solve the issue of black holes and information loss and this sort of thing. At least it would be, I certainly wouldn't say it would solve it all, but it could be an interesting proposal to be developed in that direction. Because if part of the probability flow is actually superluminal, that stops it from falling into r = 0. So if this Coulomb example extended to Schwarzschild space-time, then perhaps a black hole, in inverted quotes, would not be a black hole in some traditional sense, but you would maintain 100% of the wave function. It could be whizzing around for a particular particle. Again, this is obviously a pretty naive model, but it could be whizzing around and be able to escape with time reversal preserved and so on, which could be an interesting approach to some of the problems associated with Hawking radiation. So I guess in conclusion, my focus has been, including my previous RQI talk, which is on the volume of Schwarzschild, my focus has been different observers and treating things fully consistently in an internally consistent Lorentz, I don't know if I want to say Lorentz invariant, but a Lorentz consistent sort of way. And my focus has really been on space-time splitting and how observers make measurements. And so by this approach, by taking a wave function, determining a conserved current, and then using that to determine a bit more physical observables, such as volumes, averages, and so on, velocities, then this will work consistently when you choose an arbitrary hypersurface or an arbitrary time-like congruence representing a whole field of observers. This will be a consistent approach. As Tim reminded me, QFT is the prevailing quantum approach, or it's the most successful physics theory we have, arguably. I'd like to understand myself further the similarities and differences of that approach, and I'm just curious. My motivation has been to see how far this particular approach can be pushed, and whether my hope is that both approaches could learn from one another. If I understand correctly, state-of-the-art hydrogen modeling is the RARC equation plus corrections from QED. And so perhaps in a similar way, there could be a mutual feedback between a wave equation approach and a QFT approach. So that's the sort of hopes or nebulous ideas that I have for this. Thank you for your time.
Thanks, Colin. So we have some remaining time for questions. Okay, I have a question. A few slides back, there was this picture that looked, the one that looks like a Bohmian trajectory or something. I think you made a comment about it. This one here.
Yeah, I skipped over this. So
sorry, what are you actually plotting there?
So I skipped over this. This is out of a paper you may have seen. And this is just the double slit experiment and the Bohmian trajectories.
Oh, so that is a Bohmian trajectory.
It is.
So I thought that was something you had calculated.
I skipped through this slide without explaining it. My hope is that there'll be an analogy between, you know, this picture shows a sort of ensemble of trajectories. Or, you know, I would interpret a probability flow. A Bohmian would say that the particle would take one of these particular trajectories, and that's its real velocity and position and so on. My hope is that something analogous to this could be done for Schwarzschild. I haven't finished examining the solutions to the Klein-Gordon equation Schwarzschild. My hope is that you would have trajectories something like this. Imagine trajectories heading outwards from the black hole, and they're probably spinning around in the phi direction, which we somewhat saw before. They're moving outward radially if we're going to get Hawking radiation scaling to infinity. And they probably wouldn't move classically, just like this double slit trajectories don't move in what we would normally call a straight line. So my hope is there'd be some sort of analogy that we could do for Hawking radiation to this sort of picture of a double slit experiment. So it's a little bit of a loose analogy.
Why do you think there'll be a connection?
The connection is just taking a trajectories approach.
Okay, maybe Nick's got a question. Maybe Nick could...
Yeah. So I mean, I have a mix of comments and questions. I mean, I like that you are thinking rather expansively about these issues and trying to make connections between things that are quite different. Like if you have a single wave function versus a field theoretic approach, the whole reason that we have quantum field theory is because it's known that interpreting the Klein-Gordon equation as a single particle equation leads to all sorts of inconsistencies. So I think what you've looked at, what you've identified is perhaps perhaps these were already known, I don't know. But what I'm getting at is that some of what you've done might be nice commentary on things that are already known, as in, here's some explanations, here's some consequences of what we know to be a bad model, but let's explore it anyway, because that will show us new ways in which it might fail, or maybe ways that people already know might fail, but reworked in a new way. One thing I like about this slide is the idea of, even though I'm definitely not a Bohmian, I'm very against that interpretation, I still find such research interesting, and I think it should be done. So a Bohmian approach to Hawking radiation, I don't know I don't know if anything's been done in that area. That could be interesting. I would caution you though against being too open-minded. We have quantum field theory. It works extremely well, and it's not really open for debate as to whether that's a good theory or not. What we have is what is still to be tested is quantum field theory in curved spacetime and how it interacts with gravity, for sure. But I think that some of the connections between quantum field theory and saying, you know, a field versus a wave equation, I'm not really sure that those are going to bear fruit, except perhaps in in an illustrative sense. But anyway, I think perhaps there, I don't know, it could be interesting to look at Hawking radiation from a Bohmian perspective, but then you'd have to do Bohmian trajectories on fields. Have you looked into that at all? I know it's been done, but have you looked into that?
On fields, do you mean QFT or do you mean, what do you mean?
Yeah, because the correct theory of particles is of relativistic quantum mechanics is quantum field theory. That is the correct theory. And when you put that together, and so that's in flat spacetime. We know that works. So then the question is, what happens when you move it to curved spacetime? And we have beliefs about how that works. But when you talk about Bohmian trajectories, you can't just take the trajectories of a particle. You have to take the trajectories of the entire field, as I understand it. Have you looked into Bohmian trajectories of fields? Because it does exist, but have you looked into it?
If I think I understand, I'm still working on my QFT, and I hope to. This is actually my biggest question for the audience, which I thank you for answering. Is, you know, what's the relationship with QFT? Because as I understand, you know, the Klein-Gordon equation is seen as, you know, describing these fields and not as a single part interpretation and so on. Yeah, I just have a interest to understand this further. So no, I don't think I've done what you're saying. I was just working on the scalar wave equation, single particle interpretation first to understand as well as possible, before then moving on to really understanding how this extends to the Klein-Gordon equation as interpreted in the field theory context. So I'm wording this correctly. So no, I haven't done it, but I'm very interested.
So I would recommend against considering single particles Klein-Gordon as an interpretation. It's not. It's a different theory. And we also know that in quantum field theory, particle number is not conserved. You can create and destroy particles. And so what you have in terms of the change in norm of your wave function could actually be a result of that issue, that when you interpret the Klein-Gordon equation properly as a field amplitude, as the evolution of a field amplitude, then you get the well, you can have an indefinite particle number. And when you restrict to saying, I only have one particle, that's where you go wrong, because that restriction is not physical. And so it's going to be broken in a few areas. But I'll stop there. It's been mostly comments.
I'm very grateful for the feedback. Yeah, that's why the textbooks that are most favorable, Greiner, Schwabel, Wachter, forgive my German pronunciation, they do say that this should, even though they like the one particle interpretation more than most, they still say this is not valid for really strong potentials and so on, for exactly the reason you say, because, you know, for the reason of particle creation, annihilation, and so on. So it does, their claim is just that this works if the circumstances are not too extreme, whereas QFT, you know, does account for changing particle number and so on.
Okay, thanks, Colin. We're going to have to move on now. So let's all thank Colin again. Okay, so our final speaker for this session is Michael Good.
Can you hear me?
Yes, we can. And we can now see your screen.
Okay, great. All right. Let me take a few seconds to make sure everything's set up. Okay.
Okay, so Michael is from Nazarbayev University, and he's going to talk about radiation from an inertial horizon.
Yes, thank you. Thank you so much for having me, Tim. And I would like to thank you personally, and also Nick and Eduardo for organization and hosting. It's fantastic to be here. It's a pleasure to talk about radiation from an inertial horizon. This is work done in collaboration with several folks. In particular, I'm going to give kind of an overview of the model that I'm using. I'm working with Josh Fu, who's giving a talk tomorrow, I believe, in the Australia section. Juan Kong, who gave a talk yesterday in the Waterloo session. It's work done with colleagues at Berkeley, and Yin-Chin Ong, who I believe is in the audience right now at Yangzhou University in China, and Frank Wilczek at MIT. So It's an ongoing project with a lot of folks. So I'm in Kazakhstan and in the capital right now at Nazarbayev University. So let me give you a context. You might be asking, what is an inertial horizon? How could you have radiation from an inertial horizon? What is that? Well, let me first give a little bit of orientation. I'm going to work in the moving mirror model, which is a 50-year-old model that describes particle production from an accelerated boundary. We can imagine this all of infinity compacted into this nice conformal diagram, and we're going to a priori choose a global motion, a trajectory of the moving mirror, and then calculate some interesting observables that come from its motion. So it's a 1+1 dimensional model. It's a massless scalar field. So it's pretty simple. And a lot of the interesting observables can be computed exactly and more often than not analytically. So the motivation is simplicity. It's fundamental because it brings together aspects from quantum field theory, from relativity, from information theory, and from thermodynamics. So it really gets at the crux of this vacuum particle production and Hawking radiation. It's also experimental. So the moving mirror radiation, as opposed to literal direct Hawking radiation from a black hole, moving mirror radiation has been detected in the laboratory in the form of the dynamical Casimir effect. And there are plenty of future experiments being planned in the works right now to directly detect moving mirror radiation. So there's a lot of experimental potential here. So it makes it quite an exciting model to work with. Keep in mind this Schwarzschild diagram here, just to remember this, this form here. I will go back to it in a second, and particularly the red line, that's the, you can think of the center of the black hole. So it's a 50-year-old model. Why do we care so much about it? What's been happening new? Well, in the last several years, last decade, basically, it has been found that there's a much tighter connection between the moving mirror, in particular moving mirrors, and the curved spacetimes. So as it turns out, say for a Schwarzschild black hole, the collapse of a null shell can be exactly modeled for all times using a very particular moving mirror. So as this tends to work for several black holes and cosmologies, as well as extremal black holes. And so when there exists a correspondence between, say, a curved space-time, the radiation coming from that, and a moving mirror, it's called an accelerated boundary correspondence, an ABC. So by correspondence, I mean that the particle production is the same in each of the cases. This is the pure Hawking effect. It neglects scattering, it neglects superradiance. It only gets to the what's called the pure Hawking radiation. So a list of known ABCs in so far discovered is the Schwarzschild black hole, the Reiser-Nordstrom, the Kerr. For cosmologies, it's the particular moving mirror trajectories have been found for the de Sitter and anti-de Sitter space, and as well as the extremal black holes, and very recently the CGHS black hole. So because of the higher dimensions and the curved spacetime, it's often more complicated to work in the curved spacetime context than the flat spacetime context of a moving mirror. So this makes it easier to compute and easier to see and understand what's going on for particular questions. So to give you a little bit of a flavor of what this Schwarzschild mirror looks like, this is F is the trajectory of the mirror. It's in a light cone coordinates. This is the retarded time. F is the retarded time. V is the advanced time. And kappa here is just the single parameter of the system. It's basically the temperature of the mirror at late times. So if you recall, that Schwarzschild diagram from a few slides ago, the red line now, the center of the black hole, is actually moving. It's the moving mirror. And it's basically a regularity condition on the quantum fields, imposing that the field behind it has to be 0 because there's nothing behind r equals 0. And therefore, in a coordinate view, it's as if there is a moving mirror that is accelerating and causes the production of energy and particles and entropy as well. So you can compute the number of particles, and you can get a Planck spectra. And you can see here this Planck spectra is, has a nice temperature of kappa over 2 pi. And in the black hole case, the kappa is the surface gravity of the Schwarzschild black hole. And in the mirror case, it's just a parameter, just a free parameter that has no particular meaning. I mean, it has units of acceleration in natural units, but it is not the acceleration of the mirror. The mirror is dynamic and accelerates all the way up to infinity in the Schwarzschild case. Yeah, I hear a question maybe? Maybe it's just some noise. Okay, so the Kerr mirror is very similar to the Schwarzschild mirror. It's also written here in retarded time trajectory in terms of independent variable advanced time. It's a 2-parameter system, just like the Kerr black hole, which has mass and angular momentum. And we can find this particle production analytically. Again, this is ignoring superradiance and backscattering, but we get a Kummer function, which appropriately achieves the correct limits for 0 rotation in the Schwarzschild case. So it's a very nice model for quickly getting to the answer for the pure Hawking effect. Even and the reason you might say, how can this model possibly simulate a 3+1 dimensional system when it's a 1+1 dimensional system? It's because the center of the black hole has no dimension, and all that's needed to understand the particle production during the collapse of a rotating black hole, at least at the pure Hawking level, is the trajectory of the origin to an outside observer. So that's like a moving mirror, and it has no dimensional, and the asymmetry of the black hole itself does not affect the trajectory of the center of the black hole. So interesting enough, we can look at the de Sitter moving mirror, and it's quite a more simple situation, actually. It has 2 horizons here, and it's eternally thermal. It always gives off a constant flux of positive energy, and we've been able to find the beta Bogoliubov coefficients and compute the particle production as a thermal spectrum eternally. And we've done this for the ADS cosmology as well. So it's a true thermodynamic system. Now, for the extremal mirror, this is somewhat the opposite. It has no temperature. In fact, it's undefined temperature and kind of a weird looking spectrum here. It's a modified Bessel function. And it looks the trajectory looks again very similar to the Schwarzschild trajectory, but it has this extra term that's 1 over the advanced time and has this fancy A squared. This is the final constant acceleration of the mirror. This is for an extremal Kerr black hole or an extremal Reiser-Nordstrom black hole. The A depends upon, so it's a 2-parameter system where at extreme it becomes 1 parameter where the charge is equal to the mass. But the key thing to know here is that there's no temperature ever, and that there is a uniformly accelerated mirror at asymptotic late times simulates the extremal black holes. So, so now that I've given a little bit of intuition and background, the black hole, the Kerr-Newman case that goes to all the correct limits is a Kummer spectrum. The cosmologies are thermal for the de Sitter and anti-de Sitter. The anti-de Sitter is actually negative energy flux. but the extremals are asymptotic uniform accelerated mirrors. So now I think I'm in a position, now that you have a little bit of orientation, I'm in a position to introduce a topic that I'm excited to tell you about. Now, look at the accelerations here, right? So for black holes, as time approaches the horizon time, the acceleration goes to infinity. This is for all the black hole ABCs. Now, if you look at the extremal cases, as time goes to the horizon, the acceleration goes to some constant, uniform acceleration. Now, there are moving mirrors that model remnants and complete evaporation, and this is a case where the acceleration goes to 0. But there's no horizon, right? So as time goes to plus infinity, the acceleration goes to 0. So what I would like to do is actually combine asymptotic inertia with an asymptotic horizon. So in other words, I'd like for there to be a horizon at some time where the advanced time approaches that horizon time. And at the same time, the acceleration goes to 0. So in other words, the speed has to go to the speed of light, but the acceleration will go back down to 0. And you see this x-axis here is going to be, say, advanced time, where it starts at negative infinity and it goes up to, say, 0 time. So it's some finite number, which is just that we can just set it to 0 here, where will be the horizon time. So the acceleration goes to 0 at the horizon, and the speed goes to the speed of light. But it has to do it in such a way as to cause a horizon. So let's look at the trajectory that does that. Here I've put it as a extra term here, 1 over v squared. And it's a parameter that depends upon the scale of the system here. That's the mass. I'm anticipating that this might be an accelerated boundary correspondence, and m will be the mass of the object in space. So if we do a nice little diagram, plot the trajectory, it looks like any other black hole mirror. It has a horizon, starts at rest, begins to accelerate, and goes off into a nice horizon where left movers never hit the mirror. You don't really see anything that hints at the fact that the acceleration drops back down to 0. But you can see that hint in a Penrose diagram. It kind of doesn't want to be near the horizon until the very end of time. It kind of touches down at null infinity only at the very end. So that's a hint that there's something pretty unusual about this particular motion. So the first thing we can calculate is the energy flux from the stress tensor. It's very easy. It's a few derivatives. It uses the Schwarzian derivative. Typically in this model, we work in retarded time. So the energy flux is just the Schwarzian derivative of the advanced time trajectory in terms of retarded time. But since we're working as a retarded time trajectory in terms of advanced time, there has to be another little factor of the derivative of the trajectory squared. But it's still a Schwarzian derivative, and it's easy to calculate. And you can see that at the beginning of time, there's no particle production. It starts to produce particles, reaches some maximum, and then dips back down to 0. So you see at time in -1 here, there's 0 energy production. It actually dips below the x-axis, which is quite interesting. But ultimately at late times, it drops back to 0. So this means that the energy must be finite. I can integrate under this curve. And it turns out that when you do integrate the total amount of energy, you get a nice analytic answer. It's extremely simple. It depends upon its inverse to that scale, the mass scale, or the single parameter of the system. It's completely analytic, so it's just really nice and simple. You have to do the integration over advanced time rather than retarded time, which is easier and more intuitive, but the advanced time is still very straightforward to do. Then you have to integrate up to the horizon, not all of time. Well, so much for the energy. What about the particles? Let's compute the particle production. It turns out that that is also analytic. The particle production gives a spectrum, which is a Meyer G function. It's quite an abstract complicated function, but it is analytic, and it allows us to see exactly the particle spectra. So if you add up all the energy that the mirror is producing, say a little bit of quanta omega times the particle spectrum, and integrate over all the colors, you should get the total energy. And we do this, it's a numerical calculation, but with very high precision and very, very low relative error. And we get exactly the same energy that we derived from the stress tensor. So we know the model is consistent, and that's very encouraging. So what is going on here? Well, I've tried to put a little table to kind of give a little bit of the where this solution fits in terms of all the accelerated boundary correspondences, the ABCs. And I'd like to just go over this table so you can get a little bit of a feel for where this solution fits. The black holes, again, have infinite acceleration at the end of time. So they have a horizon, and they necessarily have information loss because the left movers just keep moving and they fall into the black hole, or they never hit the mirror. You can think of this. There's no negative energy flux, it's just always positive energy radiating. There's an infinite amount of energy radiated from these moving mirrors that mimic the black holes, and there's an infinite amount of particles. Because the acceleration just goes on forever, you can think of it like this, and the speed eventually reaches an asymptotic speed of light with an infinite acceleration at late times. Now, the extremals also have a horizon, so they have information loss. They don't have negative energy flux, just like the black hole. But the thing that's different about them is because their acceleration is constrained and it goes to a finite value, there's a finite energy production during the whole process. They still have infinite particles because it accelerates forever. It just doesn't go to infinite acceleration. Now, the remnants are much different beasts. They don't have horizons. The effervescence is the same way, no horizons. And the cost of that is negative energy flux. So at some point during the trajectory, during some time in the evolution, the black hole actually grows as it is evaporating. It actually gets more massive as it evaporates, or the moving mirror emits this negative energy flux at some point when the jerk is directed towards the observer. It has a finite energy, and only the effervescence, the ones that have complete evaporation, have a finite particle production. So they don't suffer from this soft particle divergence. So where does the inertial horizon fit in? Well, the inertial horizon has a horizon. It has information loss because clearly left movers, not all the left movers hit the mirror. And it also has negative energy. So this is it fills a nice little spot in the literature where it's a very unique situation. It has finite energy, and it does suffer from the soft divergence. That should make sense since it goes off to the speed of light, just like the extremals and the black holes. So this is information loss with negative energy flux. And so if it does correspond to a strongly curved space-time or a compact object, it potentially hints at an object that has a horizon like a black hole, but is shining with negative energy. So it's kind of like a negative energy star or a negative energy type black hole. So this seems pretty curious, pretty interesting, and it would be nice to further explore the metric that's associated with this in the curved space-time context. So I'll wrap it up there, and I very much appreciate your time. If there are any questions, it would be fantastic to get some feedback.
Thanks very much, Michael. So we have plenty of time for questions.
I think maybe Josh is.
Sorry, I can't. I don't see anyone with a hand up at the moment, so I'll start. I guess this last slide looked a little bit like a, I don't know, a white hole or something. Is that?
A white hole, you say?
Well, I'm I'm
Yeah,
not sure if I
actually,
quite understand what exactly is going on, but.
Well, I mean, so the stress tensor has this negative energy, this negative sign on the energy flux. So I'm not aware of the white. Well, yeah, maybe that is kind of like a white hole, actually. Gosh, I guess this could be an ABC for a white hole. Yeah, because it's maybe sucking in or absorbing energy. Well, or radiating negative energy. It's tough to understand because negative energy flux, while it's not unprecedented in quantum field theory, it's still kind of a mystery. A few folks think that it's related just to the lower dimensions, but in the case of the moving mirror, it's just a negative sign on the radiated energy. So in some sense, it's the worst of both worlds, where there's an information loss and negative energy flux, two things you might not want. But in another way, it's still, I think this model has a nice value because it pushes the known models to their extreme and actually finds a kind of a point where there's, the characteristics of both of these situations. So it kind of fills this gap in the literature that is just unprecedented. So it's I mean, of course, at the late times, there's no energy flux being emitted at all. I mean, it goes down to zero, so it's very negligible at late times. But at late times, it is still negative. So it's emitting negative energy flux forever, just less and less and less and less as time goes by.
Rob's got his hand up.
Yeah.
Yeah, hi, can you hear me, Michael?
I can. It's great to see you.
Yeah, it's nice to see you again. So yeah, I just, well, two questions, I guess. One is on your chart that you've got there, every one of those things has at least one X. Is there any kind of mirror where you would get a check mark in every column?
Ooh, that's a good question. I mean, okay. So I'm personally, my opinion is that effervescence are the most physical. They represent nice, wonderful mathematics with finite particles, finite energy, and no information loss. And yes, they come with a cost of negative energy flux, but to me, it seems like that is the most consistent type of model. To have, if you have a horizon and, well, okay, yeah, so I don't think so. I don't think you can have, the answer is no, because if you have a horizon, you will necessarily suffer from infinite particle production. So you will end up getting this divergence, a lot of soft particles. Yeah, so you'll end up getting soft particles.
There's no way out of that, okay. So in some sense, column 1 and column 4 are mirror images. Oh no, they're not, because remnants don't have both, but yeah, okay, so it's not exactly the same. I guess the other one that you probably might guess I would ask, based on your experience for these other objects, the mirror analogs of other objects, what do you think is going to happen to the entangling properties outside of these things? Would you care to speculate?
Let's see. Actually, I actually consider the entanglement properties. It's a wonderful point, because the entanglement entropy in the moving mirror model might be one of the most simple interpretations, particularly, well, definitely with respect to the dynamics of the mirror, because the entanglement entropy in the moving mirror model is just the speed of the mirror, the rapidity. So So the entanglement properties are quite they're quite weird, because sometimes you can just see this. Well, you just see the rapidity, the speed of the mirror. So as the mirror, if the mirror goes to the speed of light, you can see that the entanglement diverges. As long as it stays sub light speed, the entanglement is always finite at any given moment. But it actually proves to be, it's a little more harder to get an intuition for, but I would speculate that so if I look, so the divergence of this in this inertial horizon, the entropy diverges at late times. So that's a kind of a signal that unitarity isn't preserved. Of course, we already knew unitarity isn't preserved if there's a horizon, but the entanglement can be used as a nice measure of unitarity. But it's definitely an area to compute these measures and to find some interesting behaviors, and I hope to do that actually with these solutions and some more.
Okay, thanks.
Yeah. Thank you for your questions. Yeah, it's.
I don't see any other questions. I'll just. I realize there's something I don't quite understand here. So these are all mirror analogs in this picture. So in principle, one could do the experiment. One could set the mirror on some trajectory that corresponded to the analog trajectory, and you would see these effects, I guess, at least in the radiation. So how do I interpret what the negative energy flux will, what will that look like in an actual experiment?
Yeah, that's really nice. Yeah, because if you set this up as an experiment, because these are global motions, they start at the beginning of time and then go all the way to the end of the universe. There's some like local. There's kind of a low. It's how do you do this locality situation with the experiment? And so the end states are actually pretty important, especially if you. So for this inertial horizon, you wouldn't see the negative energy flux until the very end of the motion. So localizing this is an issue. You'll always have positive particles. There's no negative particles, unfortunately. But the stress tensor does indicate a negative energy, and so
am I just going to see squeezing or something like that?
This is definitely squeezing transformations. Is definitely all of these are non-trivial squeezing Bogoliubov transformation matrices. So
I get it.
I think it could be that negative energy flux is just some sort of artifact of the renormalized stress tensor, and it doesn't actually. It's like a transient, and it's just kind of a mathematical artifact. And once you actually measure particles with a particle detector and you measure their energy carried, you're just not going to pick up any kind of, in some finite frequency and finite time, you'll never pick up the negative energy flux. It's just kind of a mathematical artifact. But it could, perhaps it's some absorption of energy, perhaps it's actually a radiated negative energy. So I think it's to be seen. It's still a mystery.
I think maybe what it's saying is you'll see squeezing in the field.
Cool. Yeah, thank you.
Okay. So I don't see any other questions. So let's thank Michael again.
Thank you so much, everyone.
And so that brings us to the end of this session. So I'd like to just thank all the speakers again. I think it was a very interesting session. And thanks to all the participants who came along to see this. And we will be having another session same time next week.
So Tim, maybe you can also announce the session just in case of some people, which is also next week.
Sorry.
I was wondering, maybe you could also advertise the Waterloo session that it happens.
Oh, well, why don't you, Eduardo, why don't you advertise the Waterloo session?
So next week we're going to have exactly the same kind of day as today. We'll have a Waterloo session in the morning, which is your night, I guess, late, very late in your night. But for those of you who can come to both, don't forget that we will be having it at 9 a.m. on Wednesday, EST, so Waterloo time, which is, again, adjust to your corresponding time zone. And I'm very aware that if you're in Australia, that will be tough.
I think we've had a few people who went to both sessions, so that was
which is
yes,
remarkable, yeah.
very good. Okay, so thanks again, and yep, we'll see you next week.
Thank you, everyone.